Good morning, everybody. My name is Yuan, and I'm a postdoc at the University of Cambridge, working with Richard on utilizing modeling and simulation tools to understand the optoelectronic properties of perovskite. And today we're going to share a result, a work we work on understanding the atomistic origin of artificial glass formations in the system. So on the left-hand side here is a series of experiments performed on the mixed chloride and bromide perovskite by our collaborator team. And what he did was to first measure a set of calorimetry measurements whereby he observed these distinct phase transitions when he has either a pure bromide and a pure chloride system, as you can see here and here. And he did it for both the methyl ammonium cation and also the cesium cation. And what's the difference between these two systems is that once you have the methyl ammonium cation and when the composition X of the halide is 0.5, you do not see any phase transitions, whereas you still observe these phase transitions for the cesium cation. And sort of similar observations can be seen in the low temperature XRD, whereby you can see that for certain composition of X in the middle, when X is high, you basically have one lattice parameter corresponding to the cubic phase, whereas when X is small or very large corresponding to pure phases, you then have three distinct lattice parameters corresponding to the orthorhombic phase. And we can sort of construct a phase diagram to illustrate this, whereby basically when we have a large alloy mixing, we have this suppression of the phase transition. And to understand these phenomena, we performed a series of density functional theories calculations to understand its atomistic origin. So first, what we do here is we construct a supercell, as you can see here, of a cesium-lead chloride bromide alloy. And we started out with the orthorhombic phase, which is the low temperature, preferred low temperature phase. And then we perform a structural relaxation. And then after the structural relaxation, we realize that the structure remains orthorhombic, as you can see by the middle here, whereby we have the three distinct lattice parameters. And this shows that for the mixed chlorides, for the mixed halide system, when you have the cesium cation, the system prefers to be orthorhombic in low temperature. Whereas if we replace the cesium with the randomly oriented methyl ammonium cations, and we perform the same calculation, and then we realize that essentially we observe a cubic structure at low temperature, and because the density function calculation is done at 0 Kelvin. So what that this means is that a mixed chloride system with methyl ammonium prefers cubic at low temperature, and this sort of agrees with the experimental observation that the phase transition is suppressed at low temperature, that the system prefers to be cubic. The reason why this is the case is because I think due to the hydrogen bonding in the system, and we can measure the sort of angle between the methyl ammonium and the halide, and the methyl ammonium actually tend to align itself towards the chloride atom, which is more electronegative. And because these chloride atoms are randomly distributed in the supercell, then the MA end up overall having a random orientation, which means that they are on average end up in a cubic arrangement. So when you lower the temperature, the MA is sort of locked into these random glassy structures, whereby even if you lower the temperature, the cubic structure is retained due to the presence of hydrogen bonding and the preferential alignment of the methyl ammonium cations. So if you want to discuss more about this poster, I'm happy to talk about in the discussion phase. Thank you very much.